So thanks very much. Thank you for the invitation to come here. I'm really looking very much forward to this workshop to sort of learn more about what kind of interesting things can be done with one-dimensional systems. And so I'll present to you like a range of experiments that we've done in our lab in the past few years, and with a number of students. And so I also thank Yasu for giving the very nice introduction to what this general work is about, and so that I can more or less dive in right away. But before beginning, maybe I should also acknowledge not only the people who've really contributed to this work in particular, but those who've kind of worked in our lab in the past few years at ETH, trying to set up all the infrastructure and all the experimental techniques and generate some of the ideas that I'll be presenting to you. Okay, so the topic is Photon-Qubit, or photon light matter interactions in one dimension, and we're looking at one-dimensional circuits. So depending on how time goes, I plan to present to you 4 different little pieces of experiments that we've done. And so the first one is on single and 2 atom superradiance and their time-dependent measurement, and also the tomography of the states that get created in these superradiant processes. And sort of one of our motivations for doing this work actually was generated by the fact that still some of the ideas that Dickey presented in his original paper in 1954 on superradiance hadn't really been explicitly tested yet. And since we have lots of control in these superconducting circuits on the atomic and photonic degrees of freedom, we had a look at that. So then I'll also briefly, and so this is an experiment that is done in sort of in the fast cavity limit, or in the bad cavity limit of cavity QED. And so in the second experiment here that I'll just briefly remind you of, we've also worked in this Waveguide QED limit, where we've gotten rid of the cavity altogether, and where we've just looked at the strong interaction of qubits with a continuous mode, and where we can actually see super and subradiance, and also maybe most interestingly these photon-mediated dipole coupling between emitters. And so, like, another piece of work that connects nicely to what Yasu has been talking about is sort of our effort on trying to create time reversal symmetric single photons. And where you see sort of some of the experimental results here, where we're mostly motivated to use these time reversal symmetric photons to create entanglement over larger distances, and think about how to build up quantum networks using microwave frequency photons. And another useful element there is sort of a fast linear microwave frequency switch that if I have time, I'll get to, that we're just currently working on in our lab. Okay, and so one of the ingredients that will actually be made use of a fair bit in the experiments that I'll be presenting to you is using techniques that we've developed in our lab to actually characterize propagating microwave frequency photons using tomography techniques based on quadrature amplitude measurements that have really allowed us to reconstruct the Wigner functions of propagating microwave frequency modes. So once microwave frequency photons get released into a transmission line, and we're able to measure their quadrature amplitudes. And these types of techniques have also allowed us to measure the entanglement between photons and qubits, where the photons are not captured in a cavity propagating down a transmission line. And in this context of playing with microwaves in one dimension, we've also been able to sort of implement microwave frequency beam splitters. This is also an element that will reappear in my discussion of the microwave frequency switch, and which we have used actually to create Hongo-Mandel type of experiments with 2 single photon sources at the input of a symmetric beam splitter. And with these detection techniques, we're actually able to also fully reconstruct the quantum states of multimode fields. Yeah? So here's, for example, the density matrix of the 2 output modes of a beam splitter when it gets fed by a set of pulsed microwave frequency single photon sources. And we're also making heavy use of these parametric amplification devices that also Yasu mentioned, and maybe one recent thing that I could mention there is that that there you can look at sort of quantum optics for continuous variables, and by now we are able to create squeezing to maybe about somewhere between 12 and 15 dB of the vacuum noise that is incident on these parametric devices. Okay, so let me start with the first part on sort of the bad cavity and the waveguide QED limits. And so I think it's still fair to say that the majority of experiments in circuit QED investigate the strong coupling limit, yeah, and strong coupling is relatively easy to realize in these systems. And so here you see a typical vacuum Rabi mode splitting that you can measure when you couple a superconducting qubit coherently to a superconducting cavity. And I would say by now it's even almost unavoidable to see the strong coupling between the excitations in a single qubit and a single photon inside a cavity once you make a sample and put it into your fridge. And indeed, the student who worked on this bad cavity limit had to actually think a little bit about how to make the coupling constant of the qubit to the cavity weak enough so that you would be able to explore sort of the bad cavity limit of circuit QED. And so instead of seeing then in this bad cavity limit this nicely resolved vacuum Rabi mode splitting here, you can essentially see here this sort of EIT-like dip in the cavity transmission spectrum once the cavity is wide and coupled to a qubit with a coupling constant G, which is smaller than kappa, but where the qubit non-radiative emission rate and the qubit dephasing rates are much smaller than both the coupling strength G and the cavity line with kappa. And so we'll use this limit here to investigate Dicke superradiance and the dynamics of collective radiation emission in these systems. And then, as I said already, we'll briefly look at this waveguide QED experiments where you get rid of the cavity altogether, where you essentially let this kappa go to infinity and look at a continuum of modes coupling to two superconducting qubits. And there, yeah, it's important to point out that sort of the first waveguide QED experiments, as Yasu mentioned, were done in Yasu's lab together with Shen Tsai, and also Per Delsing's group at Chalmers is active in this direction. Okay, so we're looking at circuit QED in the bad cavity limit, and the situation that we were interested in is sort of schematically depicted here. So we take a single cavity and consider a single mode of that cavity, and we're coupling two emitters to this cavity, and we can drive the two emitters independently with radiation fields from a side port that allows us to prepare the emitters in an arbitrary initial state. And this cavity is set up in a way that it essentially is strongly coupled through one of the mirrors, so that all the radiation that might be created by these emitters here will actually leave the cavity to the right-hand side. And we can also realize a situation where the non-radiative decay rates of the qubits are much smaller than any of the other relevant physical parameters. And so here you see a picture which has been colorized a little bit from the actual device in superconducting circuits that we're using to implement this kind of device here. So what you see is sort of the blue structure here, which extends from this large coupling capacitor here to the small coupling capacitor. Somewhere there is the cavity. So this meandering line here is a lambda half cavity. So we have two artificial atoms, one at the left-hand side, one close to the output coupler of the cavity and one close to the input coupler of the cavity, and our superconducting qubits are of the transmon type, and they're colored here in yellow. And they actually have a slightly weird geometry, or at least if you look at transmon-like qubits, you very frequently see sort of two comb-like structured electrodes that are shunted by a little squid. And here you see that this looks differently. So we have these two sort of squarish electrodes, and they're sitting side by side to each other and are connected to each other in this slightly weird geometry through a squid, which sits about here. And the reason for choosing this geometry is here to choose qubit parameters which are very similar to our typical qubit parameters with same transition frequencies and same unharmonicities, but now with much, much smaller coupling to the cavity, so with small g. And why this qubit here now couples only weakly to this transmission line resonator here is the fact that essentially these two square electrodes have almost the same capacitance to the waveguide here, and so that if you have a field on this waveguide, it drives only a small differential voltage between these two little capacitor plates. And so the more symmetric that is, the weaker will the coupling be, and so here the coupling is engineered to be quite small. So then we can prepare the qubit states through these fields that we can shine from the side onto our cavity, and that gets done through these waveguides that approach the qubit here. So these green lines here that you see come up to the qubit through this capacitively coupled gate here. So that we use to prepare initial states. And then we have these red lines here through which we can send current pulses past our qubit squid loop. And these red lines allow us for both qubits A and B to tune the transition frequency of the qubits on timescales of nanoseconds. Okay, and so we're in the bad cavity limit here. So our cavity decay rate kappa is 43 megahertz. The coupling strength G, the dipole coupling strength, is about a factor of 10 smaller, so it's about 3.5 megahertz. And the non-radiative decay rates, as measured, can really be much smaller than any of the other parameters. And maybe the worst parameter here is sort of the fact that our dephasing rates are not extremely small in this system, and that will show up in some of the measurement results. Okay, and so one situation that we're interested in the situation that we can tune these superconducting qubits in resonance with our cavity, and then look at with our bad cavity and look at superradiant effects. And these superradiant effects will, in those photons, will be generated at a rate that is given by the coupling strength G and the kappa, the decay rate of the cavity. Okay, and so what we then do is, I've already mentioned it, so we have, this is an energy level diagram, a schematic one, so we have these two qubits, A and B, that sit in the idle state at two different frequencies, and at these frequencies we can now apply microwave frequency pulses to the individual qubits to essentially prepare an arbitrary initial state. You know, for example, an excited state, or a superposition state, an equal superposition state, or one with a given phase. And then we can use these flux lines to actually tune both qubits simultaneously into resonance with the resonator, or to a frequency that is very near resonance. And then these qubits will start to interact with each other through the cavity mode, and they will also then emit photons into the cavity, and these photons we're then ready to detect with our detection system. And so that's the type of experiments that we're doing here. So the first thing that we do is we actually take each individual qubit, prepare it in its excited state when detuned from the cavity, and then tune it into the cavity and just look at the radiation emission from the cavity. And here you see the measured power for qubit A and qubit B versus time, and you essentially see the time-dependent emission signal of the two emitters. Yeah? So we've prepared the qubit in the excited state, tuned it into resonance with the cavity, and then the excitation decays from the cavity at a fixed rate that is given by this Purcell rate that I've mentioned before. And so you see that the emission of the two qubits here, these experiments are done one after the other, sort of independently from each other, and the emission rates of the two photons are very similar in this case. And so to look more carefully at how different these two emission rates are from the average of the individual qubits, we've just plotted the difference of each individual qubit decay from the average qubit decay, because that's the type of quantity that we look at later for understanding the superradiance. And so here you see that there's only the two qubits actually decay, interact with the cavity field, and then decay in a very similar fashion. Okay, so that's just independent qubits, and so then the next thing that we do is we prepare both qubits in the excited state using microwave frequency pulses, and then tune them into the cavity simultaneously. And so what you then see here is sort of the first thing that you should notice is here you see the emitted power is on the peak power is on the level of 3 h bar omega per microsecond or so, and now that you start out for the individual qubits, and now that you start out with both qubits in the excited state, then the peak power will essentially be starting out to be twice as high as at the beginning. But what you then see is, and the measured data are these blue points here, and the red points are actually the what you would expect if the qubits would decay independently from each other. So this and what we are now interested in is to understand where this little difference comes about, and how this little difference comes about, and whether we can understand its size. And here this difference actually is due to the fact that the emission of the radiation from the two qubits comes correlated through the interaction with the cavity mode. And so the difference between what we observe when both qubits are in the excited state and then decay in a correlated way from the situation where they would decay individually is just shown again in this plot here. And you see that initially for small times the emission is slightly enhanced, and then for later times the emission is slightly reduced in comparison to the single qubit case. And also if you look at the dynamics, what you see is that initially the 2-qubit excited state decays at a smaller rate, and then at later times at a larger rate, again in comparison to the single qubit case. And so the question is, can we understand that? And so if you do just a simple rate equation calculation from what you would expect for the superradiant case, you would actually find this black curve here, which is in reasonable agreement with our data. But this rate equation calculation doesn't explicitly take into account dephasing of our qubits. And once you do that through master equation calculation, you actually find quite good agreement between what we measure and what one would expect. Okay, so how can we understand this superradiance of these two superconducting qubits in more detail? So the difference really comes about that if you look at the independent decay dynamics of two individual emitters, both emitters could be in the excited state initially. And so you have two excitations that you could create, or two photons that can be emitted. And these, if they're really independent, these two emitters decay independently. And an intermediate state will be with either the first qubit decayed or the second qubit decayed. And then the final state is reached by the other qubit also decaying and creating two photons essentially independently from each other. But what happens when the emitters can actually interact with this cavity mode? Instead of decaying through individually from this doubly excited state into the ground state through states GE and EG, in this cavity mode here, in this bad cavity mode, you can actually decay through this bright state. And this bright state gets created through the interaction of the two individual qubits. And so you decay from this doubly excited state into this bright state at rate gamma kappa. But once you are in this correlated bright state, this bright state actually decays at a twice enhanced rate, and this is essentially what gives rise to this Purcell decay. And so if you calculate based on these states here, the rate equations, then what you'll find is what I've indicated on the last slide. So what is also interesting that in his paper, Dickey in 1954 sort of indicated that there should be something like single atom superradiance. And so single atom superradiance sounds a bit like a strange concept, but it refers to the situation where you have two emitters that interact through a common radiation mode, but one of the emitters is in the ground state and the other emitter is in the excited state. And so we've done that experiment where we leave one of the emitters in the ground state and the other one we excite into the excited state, and then we simultaneously tune both of them into the cavity and again look at the emitted radiation. And so what we find is shown on this slide here, again compared to the situation where we would consider independent emitters, which are these red dots. And what we measure are the blue dots from the correlated decay of the two emitters from this initial state. And again, we can look at this difference here shaded in this dark orange color, and we can compare it to sort of a rate equation calculation based on this level diagram, which I've shown to you before. Or we can do a full master equation simulation, which gives us much better agreement. And so here we see this single atom superradiance effect where essentially the radiative decay happens much faster initially through these correlations that get mediated by the interaction with the cavity mode. And so what you could also do, instead of starting with these basis states, G and E, you could also start with a coherent superposition state G plus E for both of your qubits. And the way how to think about that, now you're in an equal superposition state, but that gets created in sort of a phase coherent state already. Whereas when you start with both qubits in the excited state, then this phase coherence between the two qubits will only get created through the interaction of the two qubits with the cavity mode. And again, you can look at the difference of this situation with the independent decay of the qubits and understand it in terms of this master equation calculation and also in terms of the simple rate equation. And so one of the interesting things that we are now able to do for these types of experiments, we're not only able to look at the time-dependent decay of these signals here, but we can also fully reconstruct the photon state at the output of the cavity in the superradiant situation. And so what we do is we start out with our qubits in, say, an arbitrary initial state, here the equal superposition state for both qubits. Then we look at the photon field that gets created. We detect both of its quadrature amplitudes, and then analyze the statistics of these quadrature amplitudes and reconstruct the density matrix of the emitted radiation field. And so what we then need to, what we make use of for this situation is the fact that our initial states essentially decay through this decay chain here, where the ground state creates no photon, the dark state also doesn't create any photon, the bright state, this one here, creates essentially a single photon on average, and the doubly excited state creates a 2-photon state. And so these we can actually reconstruct then, or what this the created photonic state is, we can actually reconstruct by mapping the initial qubit state here decomposed in the ground state, the doubly excited state, and the bright state, and relate that to the photon state that gets created in the interaction with the cavity field. And by analyzing the, okay, this I should have said, by analyzing this quadrature amplitude distribution according to the methods that we've developed earlier, we can actually reconstruct the full density matrix for this cavity output state, where you see here the real part and the imaginary part for this 2-qubit initial state, for the separable 2-qubit initial state. And the separable 2-qubit initial state actually turns in this type of photon state at the output of the cavity, where you see that you have this square root of 2 over 2 Fock state contribution here, which you see has the highest real part in the density matrix. And then there's also the vacuum state and the 2-photon Fock state here, and you see that for this pure state you essentially get also coherences between the individual components of the state. And so this is kind of a useful technique to really look in detail at what kind of photonic states get created in these types of processes. And we've done the same thing now for 2 initial qubit states which were out of phase, and looked at the density matrix created in a similar way. And what you see here is that actually in this case this gets preferably converted into a dark state, and this dark state doesn't create any photons, and the density matrix of the resulting state actually has a large vacuum state component and a 2-photon component, but almost no single photon component here, and the coherences you see at these off-diagonal elements. Okay, so this shows you that you can look at some sort of a basic physical phenomena like the superradiance effect in quite some detail in these kinds of systems. Okay, so to summarize that part, we've realized a generalized version of Dicke's 2-spin Gedanken experiment, so being able to start out with arbitrary initial states, with both qubits in the excited state or in equal superposition states with adjustable phases. And we've seen the superradiant decay and the time dependence of the output field, but we've also been able to look at the density matrices of the created fields reconstructed in the photon number basis, and we were also able to look at this single atom superradiance as suggested in Dickey's original work. And this could probably be extended in directions for looking at entanglement by dissipation or measurement-induced entanglement, or even look at superradiance at multiple frequencies. Okay, so this concludes this part on the low Q cavity and the circuit QED in the bad cavity limit. And so in this next set of experiments, I'll just remind you of this work that we've done on strong coupling without cavities, where we have looked at the emission of 2 emitters coupled to the same waveguide mode. And so why is this interesting? It could be used for quantum networks, or looking at photon interaction, or building single photon transistors in this kind of context. And so as Yasu pointed out in his nice introduction already, what is really essential in this context is to strongly confine your light in this one, or the microwave frequency radiation in these one-dimensional waveguides. And this strong confinement then gives rise to interference effects on a few photon level that Yasu has also pointed out, that are actually quite difficult to realize in three-dimensional systems. So for example, when you couple atomic emitters to single waveguides. And so typically, and I think we'll probably hear quite a bit in upcoming talks at this meeting, sort of typically to get reflection coefficients that are large from single atoms or single molecules is kind of challenging in these three-dimensional geometries. And so what we are therefore, and also detection is more difficult because you essentially are trying to look at the photons that get scattered into 4 pi from your single emitters. However, in waveguides, so single atoms scatter radiation or single qubits scatter radiation either in forward or backward direction. And so you can essentially see this perfect extinction. And just to confirm Yasu's results, it's really relatively straightforward to get close to 99 or better than 99% extinction of this transmitted microwave tone here. And that's really because you can couple one of these superconducting emitters very strongly to this continuum waveguide, where this coupling strength really overwhelms any of the other relevant parameters by a lot. Yeah. So here in the case that is shown here, I think the coupling rate here to the waveguide is 26 megahertz or so. And the non-radiative decay rate is more than 100 times smaller, and the dephasing rate is also very, very small in comparison to this coupling strength to this cavity here. So the photon re-emission essentially happens with unit efficiency into this waveguide. And what is nice about that is that this then allows you to actually look at more complicated experimental situations. And what we looked at motivated by these initial experiments with single emitters, but also motivated by some experiments that a colleague of us at ETH was trying to do with single molecules. So Vahid Sandokdar in his lab had tried to make an effort to couple 2 distant molecules through photon emission to each other, and that was actually quite some time ago, and we discussed that, and we figured, okay, this should be much easier to do in sort of a one-dimensional waveguide with superconducting qubits. And so we did go ahead and realize this physical situation depicted here. So there's 2 emitters, symbolized by these green dots here, or by 2 superconducting transmon qubits, that we try to place into a waveguide at a separation that is on the order of the wavelength lambda. And so one of the nice aspects is because the qubit transition frequencies can actually be tuned over a large range, we don't physically have to place these qubits at a very precise separation, but we can essentially pick one separation and fabricate that, and then we can tune both qubit transition frequencies to a certain value such that the separation effectively corresponds to, as depicted in this waveguide, 1 wavelength. And with exactly the same sample, we can do also experiments where the separation is half a wavelength or 3/4 of a wavelength, depending on the tunability of the transition frequency of the qubits. And so what you can then do if you do elastic scattering experiments, so if you just look at the coherent scattering of these emitters, and this is the same emitters that I've shown you the single scattering of in the previous slide, you can now just measure the reflection coefficient or the transmission coefficient, and you see that the width of this reflection and transmission curves are essentially twice the width of the individual emitters, yeah, which shows you this collective behavior of the 2 emitters acting essentially as one collective degree of freedom. So that's just looking at coherent scattering, but you can also look at resonance fluorescence. And so here are the resonance fluorescence spectra. And they look a little bit like Mollo triplets. But the first thing that we noticed was that these Mollo triplets are actually quite significantly different from nicely symmetric Mollo triplets that you would usually expect. And then as we turned down the drive strength, we saw that these Mollo triplets had this more triangular structure. And we're trying to figure out what was going on. And after thinking about it a bit further, we've actually noticed that in this type of system, what can happen is that if while you're trying to prepare this bright state here, and you drive this bright state, there's some probability of absorbing 2 photons and having both emitters in the excited state, which then can, through some asymmetry in the decay rates, can decay into the dark state, or where some dephasing can lead to a conversion from bright state to dark state. So when we create this dark state, we actually see the photons getting trapped in the dark state and then get emitted at a much, much smaller rate. And so this small rate emission actually results into like your Mollo triplet to be deformed and have an additional peak that where resonance fluorescence occurs at a much smaller rate given by the decay rate of this dark state. And this dark state decay rate, again in this, as also measured in resonance fluorescence, is about 100 times smaller than the bright state decay rate in this situation. Okay, and as I mentioned before, so this is the situation where you see super and subradiance at separations between the qubits which are integer multiples of half the wavelength. But if you tune the emitter separation to 3/4 of a wavelength, this bright and dark state formation mechanism is essentially switched off, and instead the emitters can actually interact with each other through the vacuum modes that surround the qubits close to their transition frequencies. And what actually happens is that through virtual photon exchange, these two qubits can couple to each other, and if you measure the resonance fluorescence spectrum in this situation where they're separated by 3/4 of a wavelength, you will actually observe, when you reduce the drive strength, a splitting in the resonance fluorescence spectrum. And the splitting here is on the order of, leads to kind of the splitting between the dark and the bright state here, and that also relates to the coupling strength of the individual emitters to the transmission line, and is essentially given by half that coupling strength. And so this is a photon-mediated dipole coupling between two emitters coupled to a common one-dimensional waveguide mode. Yeah, and so this is an experiment that we've actually concluded some time ago, and that we're just now starting to pick up again. And because we can make nice use of this tight confinement of radiation in these waveguides. We have these transmon qubits with really very nice properties and get excellent mode matching. And this allows us to look at the strong matter-light interaction even without cavities. And where I've shown to you now that we can create these super and subradiant states, and also look at this collective interaction through photon exchange. And in the future, or in upcoming experiments that we've just now started to resume, we'd like to look at correlations between scattered photons, and we're particularly interested in interactions with ensembles with n larger than 2, and consider also the multi-photon physics. So what I've showed to you was essentially all looking at the physics that occurs when individual photons interact with these emitters, because they were all in the low drive strength limit. Okay, so this concludes this part here, and I would be particularly curious if any of the sort of theoretically or experimentally inclined people in the audience have sort of suggestions of what could be interesting questions to look at in this context. And so I have a few more minutes, not too many, and so I'll maybe come to this third topic that I've advertised, and that's about shaping photons at microwave frequencies. And as I mentioned, what we are interested in is we're essentially interested in creating time reversal symmetric photons that we could create in one emitter, and then by inversing the creation process, reabsorb with high efficiency at another emitter. And so what we're trying to do is essentially create this photon with an amplitude and phase controlled envelope. And this has been looked at at optical frequencies with atoms and ions a fair bit. And there's also an increased activity in superconducting circuits to think about how to make these single microwave photons. And there's frequently to check whether these ideas work. Or so frequently coherent pulses, weak coherent pulses get used on the reabsorption side, and we were trying to think of whether we could really work with a single photon source that would allow us to create time reversal symmetric single photon pulses. And if you can do that, yeah, you can try to think about networking systems. Okay, so our approach is a little bit inspired by these Raman approaches that we know from atomic physics, and so the scheme is sort of indicated here. So what we do is, this sort of address states energy level diagram with the qubit ground state, first excited state and second excited state, and then the same set of states but with a photon in the cavity. And what we now do is we actually go from the qubit ground state to the second qubit excited state, and then we switch on a coherent microwave drive pulse that couples this second qubit excited state to the qubit ground state with one photon in the cavity. And if we drive this transition here in the right way, we can actually control the population in this qubit ground state with one photon in the cavity. And by modulating this population here and looking at the decay back to this ground state, we can actually modulate the probability with which we create photons if this qubit is coupled to a large decay rate cavity. And you can write down the Hamiltonian for this situation here and write down an effective coupling that describes this, the effective coupling between these two states here. And so what we essentially do is we can switch on this coupling strength because it's driven. We can both control its amplitude and its phase. And that allows us to control the amplitude and the phase of photons that get emitted from this decay from the cavity in the excited state back to its ground state through a cavity with decay rate kappa. And so what is also interesting is that this is an all microwave frequency controlled photon shaping technique, whereas other techniques that are also discussed in the literature use a flux tuning of transition frequencies. Okay, and what is also good is that this process, since we start out with bringing the qubit to the second excited state, it ends when the photon has been emitted from the cavity, and so the system is trapped here, and it's guaranteed that it creates only single photons. Okay, so maybe so here's a picture of the sample, and we use some parametric amplifiers and some year in between our creation and the detection part, which I think I'll skip over because I'm running out of time. And instead I'll show you just the result here. So what we do is we start out with preparing the qubit in an excited state by doing 2 short pulses on the qubit to bring it from the ground state to the first excited state and then to the second excited state. And sometimes we just do pi-half pulses to create coherent superpositions between the ground and the second excited state so that we can measure quadrature amplitudes. And then we switch on this coherent drive tone that couples the second qubit excited state to the qubit ground state with one photon in the cavity. And so, and then we measure the quadrature amplitude of this created single photon pulses. And in this case, to be able to measure these quadrature amplitudes, we actually do that with a coherent superposition state rather than with a single photon Fock state. And here you actually see our time reversal symmetric single photon pulses. And we characterize the symmetry of these pulses by calculating the overlap with the time reversed pulse. And this overlap for the better situation here is about 98% or so. So that's very good. What is also interesting, here you see a quadrature amplitude diagram which looks at the phase of this single microwave frequency pulse versus length of the pulse. And you see that in this IQ plane it essentially has a constant phase. And that applies for any of the 3 pulses that you see here. And you see that as the pulses get shorter, at some point they are limited by the cavity decay rate. So our process stops to work well for short pulses. And so then with the same technique that I've mentioned to you before, you can also fully reconstruct the density matrix in these 2 situations. And here you see a density matrix for a single photon pulse and for coherent superposition with the vacuum. And you can measure the second order correlators from the moments distributions, and you find that the G2 is really quite good. It's close to 0. The state fidelity is not tremendous yet, and we're trying to figure out why it's limited at these values. And these are the numbers for the single photon Fock state here, and the corresponding numbers for the equal superposition state. And so currently, one of the culprits for the imperfections are the fact that our qubits have not so good dephasing rates, where the dephasing types are on the order of a few hundred nanoseconds for these particular devices. And so one other thing that we did to kind of demonstrate this tunable coupling and its phase and amplitude tunability is we have decided to make qubits with a number of peaks in the probability distribution. And so this here is a single photon pulse with 6 peaks, and we actually have full control over the phases of these individual peaks. And so we, for example, decided to swap the phase of the second pulse in this photon, and so you could then do interesting things with these states. For example, interfere these 2 types of states at a beam splitter and look at the physics of that if you were desired to do so. Okay, so I think I'm sort of out of time and will not tell you about this beam splitter or the switch experiment here, which essentially is an extension of what we did on beam splitters before. So you combine 2 beam splitters in series with each other, and you link them up by two tunable resonators, and that allows you to switch microwave frequency photons around in an active fashion on such a chip with nanosecond timescale resolution, which might be quite interesting for networking applications. So okay, so to summarize, so we've looked at the superradiance experiments, in time-resolved experiments, and in tomography. I've reminded you of our Waveguide QED experiments and where we want to go with it, and I've given you an idea on how to create time reversal symmetric photons, which we intend to use in these quantum networks. And yeah, I didn't have time to really talk more about this microwave frequency switch, which can be nanosecond fast. It can be used for both single microwave frequency photons, but it can also switch larger fields. So currently, for the design parameters that we've realized, we can switch maybe a few hundreds of photons at the same time as well. And you can turn these switches also into nonlinear switches or tunable beam splitters. And so I think it's an interesting direction to look at further. And so with that, I would like to thank you for your attention and thank the guys in our lab for contributing to this work. Thank you.
Thanks a lot for this very nice talk.
In the first part with the superradiance, as you mentioned, there's always subradiance and superradiance coupled, but you didn't seem to see much of the subradiance effect. So this second pass cannot be completely vanishing, especially in the decay part. When you excite one atom, you're in a symmetric superposition of dark and bright state. So half of the time you should get a very long lifetime.
Yeah, so the thing is that I think one of the aspects that is important is that we're not seeing, so since we're looking at the photons, yeah, so when we're, for the fraction of the time that we're truly in the dark state, we don't see the photons, yeah, at all, yeah, so they're stuck there and they reduce the emission rate, and this we see in our output data. And then the second aspect which is important, which actually matters and which gives rise to these differences in, for example, what you expect on a rate equation calculation and from a mass equation calculation, it's that one of the important mechanisms that mix bright and dark states is this dephasing, which in this experiment was not negligible. Yeah, so while you sort of create the dark state itself sort of turns into a bright state again because of dephasing, which is local to the qubits. And so this is something that is important in this situation, and that makes it a little bit less obvious to disentangle the two paths on your decay, where you're right that you go through or that both pathways could in principle be possible. And I think the data is not so instructive on that level because they get mixed in this way through the dephasing mechanism.
I mean, the other question related, maybe purely technical, but both of your qubits or emitters are within a wavelength in real space. So this direct type of coupling plays no role in your case?
Yeah, so
they don't see each other.
Yeah, so this you can check for actually, and in experiments where the emitters are closer to each other, you typically see interference between the direct coupling between the emitters and between the radiation-mediated coupling in the emitters, which is interesting to look at. But in this case, this direct coupling was very small because they're physically quite far away from each other.
In your mono triplet, you saw this trapping in this dark state.
Yeah.
Just of curiosity, do you know if the steady state is actually entangled in this case?
So yeah, one of the experiments that we would in principle be able to do, and that we looked out to do in a different setting, was to be able to maybe directly reconstruct the density matrix of the 2-qubit state that you would create, and that would be interesting. So here we couldn't do that because we didn't have the ability to read out the qubits individually. But I do think that it should be entangled if you were able to look at it. If you can sort of separate out this part and separate it from the bright state part and just do tomography on it, then you could verify it. And if you, for example, do this not in the continuum, but in a sort of in a bad cavity where you can detune the qubits, you could sort of create the dark state, switch the coupling from the field, and then do tomography on the resulting state. And in the good cavity limit, we've done that, and we've looked at the one of the 2 and 3 qubit entanglement that gets generated in the bright state interactions. Yeah. But that would be interesting to look at.
So, do you find that superradiance leads to non-classical light?
Yes, I mean you've looked at, for example, where we've reconstructed the density matrix. Yeah, so this is a okay. So the density matrix was not a density matrix of some coherent or Gaussian state, but okay, we haven't reconstructed the Wigner function for it, and we've not looked at some whether it did go negative or not. But depending on the starting state, I would say it should create non-classical light, yes. But we haven't explicitly verified that, so maybe that's something that we could do based on the data that we have already.
I mean, I think from the density matrix, you reconstructed this density matrix of photon states, and I think
Yeah.
with this, it's non-classical.
Yeah, I would.
Finite number of photons in there.
Yeah, I would also say so, but so typically if you just calculate some measure or so, then it also depends on how pure your density matrix is and what kind of maximum likelihood you take and what the fidelity of the state was, and that's the only reason why I was a bit careful. So I think it should be the case, but I'm not sure whether I could guarantee that it is actually the case based on the data that I have.
Just a general question about the last slide that you had, the microwave switch.
Okay.
So how many knobs are there on that switch?
Okay, so so what you have here, so the green parts are microwave frequency resonators with a little squid array. There's a flux line here, and what you need to do is sort of in the transmission mode, the photons just enter from one of the input ports and pass through both of the cavities on resonance, and then recombine through this lower beam splitter. And then if you pulse both of these cavities away from resonance, then actually the mode will get reflected and interfere at the output port. So there's two input ports that you drive currently, and we've just operated sort of in the classical regime for switching, but you could also change the transmission matrix of this sort of on the spot. Yeah, in the end, you could look at it like as a sort of a tunable beam splitter also. So it has some beam splitter action. But what's maybe more interesting is also because it could be nonlinear, it could also be sort of a nonlinear beam splitter if you adjust it in the right regime.
But I need just one knob to change the...
Yeah, okay, so the thing that we wanted here really also was that we wanted to be able to to separate the different ports in a meaningful way for us, yeah. And so this is this beam splitter also has an extra phase shift of pi½ in comparison to a standard optical beam splitter. And okay, so this is sort of kind of new, so something that we've just started in the beginning of this year.
Okay, so I think we should move all further questions maybe to the conference break. And thanks, Andreas, again. And